Okay. Well, good afternoon, everyone. So let's get started. This is our second lecture. Can you hear me well?
Yeah.
Okay, good. I also sent out invitations for if you want to join it online. We actually do have a limit, I think, of 50 people who can join it online. So, I think there is like around 10 of you online right now. So if you want to join online, you better do it soon while there is still space there. Okay. So let's get started. Today, the second lecture, and today we're going to talk about descriptive network analysis. So, overall, this course, the way we try to build it is such a way that it will provide you some, will teach you some capabilities, and so it will provide you technical knowledge enough for you to do like network analysis. And so the previous lecture was pretty much an overview lecture, so we just tried to give you an impression of what network analysis is and what network science is. Today we'll just jump into actual practical techniques on how to do things. Also notice that on the slides, sometimes at the bottom of the slide, I will be showing like a command that you can use in R within the iGraph library to actually sort of calculate that particular value we're going to be discussing. There are also, if you're using Python, there is, the similar libraries exist in Python. But again, for this class, I would strongly recommend and encourage the use of R and the iGraph library. Okay? All right, so let's get started. And I'm using today a little bit different system, so it might take me a few seconds to get used to it. So what we're going to do today. So first of all, I'll give a brief introduction on graphs, and then we'll talk about degree distribution and what it is and how to calculate it. We'll talk about path length within a graph and how to compute average path lengths. We'll talk about clustering coefficients, and we'll see what those values are within the real networks. So that's the plan for today. Okay, now for those of you who actually have a strong mathematical or computer science background, if you're still in the audience, that might be a little bit boring, but I still want to go over this so we do speak the same language. Those of you guys who are not familiar with this terminology, please listen carefully, and if you don't understand something, just ask me, or later on look it up in the books. These are sort of the basic things, but we need to know them in order to move forward with mathematical formulations within the network. Okay, so first of all, a graph is another pair of two sets. It's a set of vertices and a set of edges. And so this is sort of, very, very simple definition. And as we discussed previously, the graph, the notion of graph and network, they're interchangeable. So sometimes we're going to be talking about graph, sometimes we're talking about network. Again, graph is a little bit more mathematical notation, and so here I define a graph, but network is exactly the same thing, right? Now, when we want to define an edge of a graph, an edge is usually defined through the pair of vertices. And if it is a directed edge, if there is a sort of an arrow on the edge, then it is ordered pair of vertices. Now, there is a dual representation for graphs that we can use, right? We can actually draw the graph and show it as nodes connected by edges, but the equivalent alternative representation is given by an adjacency matrix, right? And here I'm showing you an adjacency matrix. And that matrix, in particular, if the graph is unweighted, so if there is no weights on edges, this matrix is binary matrix. It has only zeros and ones in it. And if there is a connection between two nodes, the matrix has one in that location. For example, node 1 and node 2 are connected here, right? So right there, on the intersection of rows and columns, there is 1, okay? But there is no connection between, say, for example, 1 and 4. Nodes 1 and 4 are not connected in the graph, so it's 0 in the matrix. Now, very important thing here to notice is that this matrix is symmetric, right? So if I draw a diagonal, then the values above and below diagonal, right, they're identical, so it's symmetric. And it's going to be symmetric for any undirected graph. So if there is no direction, preferred direction, the matrix is symmetric. And the way to understand it, of course, is, okay, if there is a connection in between node 5 and node 1, here it is, right? There is an edge between node 5 and node 1. Well, of course, there is an edge in between node 1 and node 5, right? So, I mean, it's sort of obvious, but it's something to keep in mind. Now, if we look at the directed graph, matrix, that adjacency matrix that can be used to represent this graph, is not symmetric. So if you look at this matrix and just sort of visually draw a diagonal on it, you will see that the filling is different. Now, let's see how it is actually represented. The way to read it is the following. Every row of this matrix corresponds to outgoing edges. So, for example, if we take node 2, the outgoing edge is to the node number 4, to the node number 13, to the node number 8, node number 9, and these are those non-zeros. And I put here stars instead of just binary zeros and ones, but these are those non-zero values that corresponds to outgoing edges. Now, so every time you want to see outgoing edges from nodes, you look at the rows of the matrix. Anytime you want to see an incoming edges, you look at the column. For example, if I take node number 12 and I want to see which edges are incoming on the node number 12, or incident edges, so they're going to be an edge from node 7 and they're going to be edge from node 2. So here I select column number 12, and yes, I do see an edge from node 2 and an edge from node 7. Okay? So rows, this is sort of, you can think about this outgoing, and columns are incoming. Now, again, if a graph is undirected, so an edge does not have an arrow, which actually means the connection both ways, then of course this matrix will become symmetrical. And the way we write it is Aij, and the way to read it is as a connection, an edge from node I to node J. Okay, any questions here? No. All right. Good. So, a few more definitions. Two nodes or vertices are adjacent if they share a common edge, right? So, node 4 and node 3 are adjacent because they're connected. Node 4. I'm sorry? Yeah. Node 4 and 5 are connected, they're adjacent, right? But node 6 and node 1 are not adjacent. So an edge and a node on that edge called incident. So if this is an edge, these are three incident. I'm sorry, if this is a node 5, there are three incident edges for this node. Now, the neighborhood of a node, and we'll use this Greek n, is a set of nodes that are adjacent to a vertex. Again, sort of obvious definition. If we take a node number 4, for example, then the neighborhood of this node will be node 6, 5, and 3, right? So all these guys connected. If I take node 1, the neighborhood for node 1 will be nodes 5 and 2, right? So that's the neighborhood for node 1, and this is the neighborhood for node 5. Now, degree of a node is a total number of nodes adjacent to it, right? So degree is just total number of connections. If it's social network, it's total number of your friends. If if it's phone call networks, it's total number of people you're calling to, et cetera, et cetera, et cetera. So the degree of node 4 is 3 because it's connected to 3 other nodes. Degree of node 1 is 2 because it's connected to 2 nodes. Degree of the node 6 is 1. And one of the important properties or for the network, metric for the network would be an actually node degree distribution, which is how many nodes of certain degree we have in the graph. Like how many nodes of degree 1 are in the graph, right? How many nodes of degree 2 in the graph? How many nodes of degree 3 are in the graph? Say if there is a lot of nodes of degree 1, it means your network, your social, for example, graph is a very lonely place, right? It means that a lot of people could just have one friend. And so when we're talking about those numbers, that's a distribution. For every distribution, you can calculate things like mean, median, average. So in this case, if we calculate average, the average for the node degrees is just given as an sum of all the node degrees in the graph divided by the total number of nodes. Right? So it's just nothing. Nothing special in here. But what's interesting is that one can show and prove that within a graph, the undirected graph, the total sum of over all node degrees is equal to twice the number of edges. Now, I'm not going to prove this. I'll just sort of demonstrate it for you briefly. But if you want, you can prove it yourself. So think about it. Here is a graph. 2 nodes. Sum of the nodes degrees. So the node degree here is 1. Sum of it is equal to 2. It's twice the number of edges, right? Or if you wish, here is another graph. Every node has a degree 2. So the sum of all node degrees here is 6. Well, there are 3 edges, so 6 is 2 times 3. And so on, right? And I mean, that's sort of obvious because every node, every edge that starts at one node have to, every node actually contributes. If you think about it, there is when you bring a node in the graph and there are certain stabs in there, and there is another node and there are stubs in there, and so every node contributes this sort of 2 stubs to form an edge, right? So anyway, the bottom line is if you want to compute an average of a node degree within the graph, it is very simple. It's very easy. It's twice the number of edges divided by the number of nodes. Okay, so very, very simple formula. Now, if we have a directed graph, right, so we do have direction on the edges, then we're going to talk about sort of 2 different metrics. For every node, there is an incoming node degree, right? Incoming degree, so it's the number of edges that are incident, that are incoming toward it. And there is, and so this is this blue one. And there is also outgoing, right? So this is a number of edges leaving the node, right? And it, of course, doesn't have to be the same. Then the total node degree will be the sum of those 2. And you can calculate also average in degree and average out degree. Okay? And again, sort of simple, trivial, but interesting fact that, of course, the average of the in degree will be equal to the average of the out degree. And the reason for that is because the total sum of all in degrees will be equal to the total sum of out degrees, because every edge starts and ends on the node. So otherwise it cannot happen, right? So these are like simple facts, but they're very, very useful. Will be later on in understanding networks. So now getting to distribution. And this sort of property, the distribution, we're going to be using all the time. So if, again, K is an is a node degree, ki is a node degree or degree of the node I, right? It actually tells you, how many neighbors the node has. And it could have, within a network, from sort of 0 neighbors, right? If it's disconnected node, it can have 1 neighbor, it is connected with 1 neighbor, and et cetera, et cetera, et cetera. It can have up to n-1 connections now. And if it has n-1 connections, so it is connected to pretty much everybody else, in the graph, right? If there are n nodes in the graph. So we're going to define total number of nodes as just as n. And then the degree distribution, by definition, is just how many nodes of different number of degrees we have in the graph, right? So you could think about it the following way. So we have, like, if we look here, we have 1 node with degree 1, right? We have 1 node with a degree 3, and we have 2 nodes with a degree 2. Typically, when we talk about distribution, it has this probability sort of connotation to it. And usually distribution as defined not just as a number of nodes with of certain degree, but as a fraction of the nodes with a degree, right? So it is just the number of nodes with that degree divided by the total number of nodes. And so probability distribution is the total number of nodes, the fraction of the number of nodes with a particular degree divided by the total number of nodes. And so in this case, in the case of this picture, right, there is 1 node with degree 1, and so out of 4 nodes, so the distribution here is 1/4. There are 2 nodes of degree 2, so it is 2/4, and there is 1 node of degree 3, is again 1/4. Now the way to interpret this, and actually this is a nice interpretation, also quite useful, is the following. If you randomly select a node from the graph, what is the probability that is going to be of particular degree? Let's just think about it for a second, and I'll again spend some time on this today. Later on, we'll be just using it. Let's say you're randomly picking up a node from this graph, right? So what's the probability of picking up any node in this graph? Well, there are 4 of them, and if we do uniformly pick up uniformly at random, the probability of selecting any of those nodes is 1/4, right? So 1/4 the probability of selecting any of the nodes in the graph. Now, let's see, how many nodes of degree 1 in here? It's just 1 node. So what's the probability that we select a node with degree 1? Well, it is 1/4. How many nodes of degree 2 present in this graph? Well, there are 2 of those. And so if we're randomly selecting a node, we could select either this guy or this guy, and in both cases, it will be degree 2. So there are 2 options, and probability of selecting each of them is 1/4. So the probability to select any of those is 2/4, right? Well, and the same thing with this guy, right? So the probability of selecting a node with degree 3 is just 1/4 because it's only 1 node like that. So that's a distribution. Now, if we have, for example, this weird graph, circle graph, where every node has exactly the same degree, well, the degree distribution will look like this. It's 0 everywhere except number 2. And of course, the probability of selecting, when you randomly select a node from this graph, it will always have a degree 2. And so, that's why the distribution has a value of 1 here. Any questions about this? No. Good. Moving on. So now I'm going to be showing a few examples using this node degrees and degree distributions. And again, what I wanted to notice is, well, first of all, how visualizations are done, and second is how I use sometimes iGraph, right? Because that's sort of probably the most practical hints you're going to get from the lecture. So this picture, it's a very famous graph that exists in an iGraph package. It's called Karate Dataset. And to get it, you can make a command, in iGraph data. So you have to load library iGraph data and just say data karate. It will give you the data set, and then you can actually plot it, right? And this is this is a network view of that data set. It's a network of 34 people. In fact, these are students of a karate club that was studied by sociologists, and we'll be coming back to this graph over and over again. But the story is that this karate club at some moment split into two because the instructors wanted a divorce, right? Wanted to be separate, and part of the students went with one instructor, another part of the students went with another instructor. What we see here is before the split, the friendship pattern within that karate club. And sort of the sociological longitudinal study was like, okay, if we look at this friendship pattern, could we predict the way the group will be split later on, right? And we're going to use this example many times, in particular when we look at the community detection. Anyway, here it's just visualization. And you realize by looking at this, if you look carefully, that there are some nodes here that have higher node degrees than other nodes, right? It's node 33, 34, and node 1. Very good way to show this, to visualize this, is by scaling the nodes according to their degree, and that gives you sort of this nice picture that tells you, okay, compared to between different nodes, sort of which nodes are have the highest degree, like central in terms of the degree. And you realize, okay, these are two major nodes here, right, and the big node here. But the majority nodes have very low degree, right? So visually, it's actually a very good technique to scale the size of the node by the node degree. So this is a distribution. And again, within iGraph, it's very, very easy to create a distribution. So what we see here on this distribution, that of course majority of the nodes, majority of the students have two connections, right? Friendship connections. That's again, with the instructors, that sort of means your students, they know instructor, they don't probably know the rest of the students in the class. And there are a bunch of, there are several nodes. Actually, in fact, this is one, right? So there is one node, and this is exactly count. This is not probability. There's one node with 16 connections. There's one node with 17 connections, right? So majority have low node degrees. There are some high node degrees. Now, this is a little bit different graph. It's also part of that package. It's called Yeast Graph. Nodes are molecules here, and edges are bonds here. And you realize, again, looking at this graph, you realize that there's probably a lot of dense connections down there, which we cannot see within this visualization. But one thing which is obvious is there is still quite a few nodes with a low degree connections, right? So sort of nodes of the degree 1 or maybe 2, right? They're all over the place here. So one of the ways to actually understand the graph without drawing it is by creating this degree distribution plot. And again, like here, we can still draw a graph. In many cases, if you try to draw a graph, say for the connections like Facebook or Contact friendship, you most likely fail because it's just the graph is too big and you'll see like one sort of hairy blob, but you'll not understand anything from the graph. So instead of actually drawing and plotting graph, it's good to just calculate certain statistical properties that will tell you a story about the graph. But the way to learn how to do this is actually draw the graph and then just calculate those properties and then just sort of see how what the connection between them and what you see on the graph. So for that graph, this is a distribution of the node degree. Again, you can actually easily calculate it by the command degree distribution. And what we're seeing here is that yes, indeed, majority of the nodes, right, have degree 1. Majority of the nodes have degree 1, and there are some nodes here with a higher degree that's probably belong to that core of the graph, but majority are actually have very low degree. Also notice the sort of interesting shape of this degree distribution, right? It sort of starts very high and then drops down and then becomes very, very small. Again, which means right there, this is a high probability of the nodes having those degrees. The majority of the nodes have degree 1, 2, 3, 4, 5, but then it actually drops strongly, almost to 0. And then we just have like, a few nodes like with a degree 58, a few nodes with degree 43, and again, we have a few nodes with degree like, 104, or 110, 118. Now, and this curve, we actually talked about, this type of a curve last time, and that's a power law curve, and we're going to talk about it a little bit more now. Now, this picture is actually generated for a much larger graph. I'm not showing the graph because, well, again, it's a very big graph, and you cannot show it. But you realize that within this larger graph, there are some nodes with degree, well, probably around 650, right? And there are some nodes with degree 500, etc. So it means there are thousands of nodes in this graph, and it's already very, very hard to draw it. You can also see that in the graph, and this is a degree distribution, right? There are some nodes with a very high degree, and in fact, those nodes are called hubs, right? Because they have a lot of connections. And at the same time, majority of the nodes have low degree. And if you look here, this is actually corresponds to the degree 1, right? So majority of the nodes have degree 1. It's very hard to see anything on this on this picture. You would assume that if you wanted to like sort of have a continuous representation of this, that it looks something like that, right? So it's a curve very, very tightly attached to 0. Now, for this type of graphs, the way to do this is by creating what's called looking at the graph in a log-log scale. And so the idea would be to actually going and taking logarithm of x value and logarithm of y value. Now, when you do this for this particular type of data, what you're going to see is the following. It should come, at least with some surprise to you that it's almost a straight line here, right? So, aside from the noise of the network and the fact that the network has a finite size, this is sort of almost a straight line. Okay, I cannot draw a straight line here. Right, almost a straight line. Again, my straight line is got bent. All right, how's that? All right, so it's almost a straight line. So the question is, what's so special about this distribution that in log-log scale, it is a straight line? Can you think about some sort of, mathematical formula that, in log-log scale will give you a straight line? I'll pause here for a sec.
AX minus B, minus A.
Right, so x minus b, it is right here, right? So that's the formula that gives you this sort of the line. But the question I have is, you get this line in the log-log scale, right? But what kind of formula will be, ooh.
On the original, yes?
Yeah, on the original one, right? So what kind of sort of functional dependence are we going to have here, such that when we do log, it will become sort of ax plus b, like you said. Does it make sense, what I'm asking?
Yes.
So let's see, if function... Okay, actually, this is a good idea. Look, if, for example, I say right here, y is equal x to the cube, for example, right? Then I take log y is going to be equal 3 times log x, right? And if this is my new sort of y prime and this is my x prime, okay, I'm getting there, right? So it's going to be a linear dependence. So if we have some sort of this stuff, it's going to be linear dependence. The only problem here is, this sort of y prime equal 3 times x prime. What angle will this curve have? I mean, it's a line, but it's going to be growing, right? And we want it decreasing, so we need to have minus here, right? And for this, for minus to be in there has to be minus in there, right? And there is a little detail that it also has to be, it has to be sort of shifted a little bit, lifted, but that will happen from some normalization constant there. Okay, good. So that's actually exactly how it works. And what we just described is called a power law distribution. So when you have this distribution function probability depends on node degree, and this dependence is given to you by power of the degree. So this is k to the minus gamma. You can write it as 1 over k to the gamma, and c is a constant. So it is, it can be k to the power minus 2, or k to the power minus 3, or k to the power minus 4, whatever, right? All of those functions, if I draw this p of k as a function of k, will look like that. But if I draw them in a logarithmic scale, sort of log, then they will look as a straight line. And depending on this value, the angle will be different, right? It's going to be this way, or that way. All right? So, but the key message here is the following. If you see, network, if you see a distribution that looks like this, right, sort of dropping really fast, try to plot it in log scale. And if you see something that resembles a straight line, well, then you have a power law. Now, of course, there are more mathematical treatment of that for that, and we're going to talk about it in a second. But just to give you sort of another idea, like imagine that if you can say, okay, look, when we have something that decreases really, really fast, maybe it is something, some function like e to the minus x, right? Now, of course, and it's shifted. Let's say if it is just e to the minus x, it has to go like this, but something exponential decrease. Well, if you take logarithm, you realize it's not going to look as a straight line in a logarithmic scale, right? So it is only if the function has this form, it's going to look as a straight line in the logarithmic scale. All right? Now, to be a little bit more precise, we were talking about node degrees, right? And that's why we use the notation letter k, node degree. And letter k, as a node degree, it is an integer. So it can take values 0, 1, 2, 3, etc. Now, honestly, working with discrete numbers is not very convenient, especially if you want to make certain formulas work. And so one way of dealing with that is to actually replace them with a continuous numbers, with a continuous variables, like with some variable x that can take any value, and then replace sort of summation by integration, and then do all computations using this sort of continuous algebra, and then map it back into discrete if needed. And you'll see a lot of this type of tricks. So power law as a degree distribution, now if I can put it as a function of x, right, it just means it's going to be continuous now, smooth curve. It's just given by this cx minus gamma, right? It's just instead of instead of k, I'm using x, understanding that k is an integer and x is a continuous value. Now, I'm putting here x greater or equal than x min. Well, we'll need to define some sort of x min because, again, if we look at this as a law, a power law, when x equal to 0, this function will diverge. So that's not what we want. So we need to start with certain value. And it's also good to have certain values here because if you notice, I go back a few slides. I was trying to draw a straight line here, and these guys are kind of throwing me off the straight line, right? The straight line really exists somewhere, right there. So x min, this is probably that sort of minimum value from which your function will obey this power law distribution. And in real life, again, it's the world is not perfect, so somewhere for low degrees, you will not have that. You will not have that. If your graph was infinite, then yes, it would look like a straight line. But again, in many real situations, it's not. So typically, when you start mapping it, you will have to start mapping it from certain sort of minimum value from where the dependency starts. And of course, you can just eyeball the graph and say, okay, look, okay, it feels like from here is the right place, so let's just start mapping from that point. But there is a little bit more mathematical way of doing it. So let's take a look at that. Oh, okay, and before we get into there, if we have this power law again, so this constant c, the coefficient, we can actually calculate it if needed, because since it's PDF, right, probability distribution function, the total integral underneath it, right? So if it's PDF, this whole thing underneath it has to be equal to 1, right? And with integrals, the great thing, you can actually easily compute this, and you can do normalization. Now, this is theory. In practice, we're not going to do that. In practice, computer will do it for us. So the way to do it is the following. So there is a sort of very, very nice and standardized approach of how you can actually calculate the parameters of the mapping curve, parameters of this mapping function, using some statistics and what's called maximum likelihood estimations. Now, if you're not familiar with this, don't be afraid of those formulas. Again, I'll just talk about sort of basics of why this works. If you're interested, you can dive into more of mathematics. The key here is this, so it's called maximum likelihood estimation of parameters. Метод наибольшего правдоподобия. So the idea is the following, that you actually get data from different observations. And what you want to make sure is every time you get a signal from this observation, it actually maps or matches your your model. And the idea is the following, that every signal, every data point has to contribute to the probability of the correct values in your model. And so what you're saying is the following. So given the parameter of the model, and in our case, there are two parameters in the model. There is a parameter which is gamma, which is the slope of the straight line, right? Which is, the x to the power minus gamma. So this one parameter is this gamma, and another parameter is this x min, or point from which we're starting mapping. So given our data and giving those parameters, what we're trying to do is we're trying to calculate or estimate the probability that if we had a model with a parameter gamma, the probability that it will generate those type of points that we have. All right. So if we have a model, if our model correct, it would generate certain type of data points. Now, we actually have sort of a reverse problem. We have data points, and we try to predict the value, the parameter of the model. That's done through sort of Bayesian bias theorem. I'm not going to go into the details of that. Just, trust me on that. But if the events are independent, and so every data point is independent within our data set, that's how it works, then this probability can be calculated as a product of probabilities generated by our model. And then we want to maximize this likelihood. Maximizing really means, taking derivative, equating it to 0, and solving. So we're pretty much going to be doing this dp over d gamma equal to 0. And solving it, we can calculate the parameters. Notice that there is a dependence on x-min. Now, there is a way to select it. We're not going to talk about it. You can look it up in the manual how you're going to do this. But again, the good news, you don't really have to do all this computation yourself. Within iGraph, there is a function which is called power law fit, and that function can either automatically determine for you x-min, or you can provide x-min, but it will compute this value gamma. So you give it the data, you get back the gamma. Now, you could actually do it by hand, right? You say, look, here is a graph, here's a straight line. I can actually just sort of do like linearly squares or other sort of ways to map straight line to the data. And you can actually do it. Now, the only problem is the quality of this map, of this matching, will not be very good, right? Because the data is noisy, your results will not be very accurate. But you can do that. So the better way is through the use of this type of formula, and that's what's sort of given to you within this power law fit. Why am I so sort of concerned about finding this value gamma, the parameter gamma, this x to the minus gamma? Well, because it happens that this gamma value is quite universal across all kind of functions and all sort of type of applications, right? And typically, it is around 2, 3, 4, right? So we'll see at the very end of the lecture examples of the real-world network where this gamma has values in between like 2 and 4. And it's actually surprising that the majority of the network that occur in nature that we meet, they do have that value. And in fact, next time we'll study a model that predicts gamma to be exactly equal to 3. And it seems like in many cases this model does a very good job matching the real data. But sort of this distribution p of x to the power of gamma to the power of minus gamma is the sort of the signature of power law, and it is sort of one of the properties of this complex networks that you always see, right? And that leads, and we're going to see it eventually, to the existence of hubs or nodes that are very, very highly connected, and the existence of a large number of singletons or nodes with a small connectivity patterns. Here's a few examples, like from real life. Now, these are, this goes back sort of to 99. Of course, there has been like a lot of results like that since then. But this is a publication, like one of the first publications, historically one of the first publications about complex networks. And if you look at this, for example, what we see here, this is so-called actor collaboration graph. Now, this is a graph that has actors, Hollywood actors as nodes, and they're connected by edges. And connecting by edges meaning they were in the same movie, right? And this is like 200,000 actors, and they go through like history. And for that graph, for example, average node degree is 28. So on average, sort of an actor was with other 28 movies. It was actually with 28 other actors in different movies. And if you calculate gamma for this graph, it's 2.3, right? Now, there is this sample of World Wide Web. I mean, imagine this paper was done when the size of the World Wide Web, right, internet as we know it, was only 300,000. So that was it, right? It was just pretty much the beginning of the web. Now it's billions and billions of pages. Back then it was 300,000. And for that, for that time, again, average number of pages a page was connected to was 5, and the gamma, the distribution, the coefficient of the distribution was 2.1. And there are many other data sets like power grid data, et cetera. But the point is, if you put it in the sort of log scale, what you see here are these straight lines, right? Which is amazing in the sense that thinking about that, it is very, 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 very different applications and domains. Here is another graph for a sort of bigger part of the web, also a kind of famous graph from the paper by Broder, in degrees and out degrees. Again, you see that it's sort of getting along the straight line. The in degrees and out degrees actually do have a little bit different distribution. So that's it with degree distribution. Before we jump into the sort of next subtopic, any questions here? All right. Too slow, too fast, too boring, obvious, too complicated.
No, it's okay.
It's okay. So you're surviving. All right, good. Again, just to remind you, so during the course, we'll ask you to do homeworks, right? And within the homeworks, you'll have to practically compute those things. At the end of the course, there is an exam, final exam, that is more of theoretical thing where we can ask you questions from the theory. There is no deep theory in here that we're presenting, but it's more of sort of a knowledge, right? And I can ask a question like, okay, so why is power law so important, right? Or what does power law tell you about how is the power law connected with existence of the hubs in the network, right? Things like that. So, but now it's, right now before that sort of final, and that's going to be in 10 weeks, it's sort of your time to ask me questions. So if you have questions, don't be shy, ask them.
На самом деле есть один, то есть он скорее не как вопрос, я не очень понял вот метод максимального правдоподобия, честно. То есть вот как он работает, то есть как формулу записал, а вот как понять, почему именно такая формула, честно. Вот.
Okay, got it. Ilya Andreevich, are you there?
Yes, I'm here.
Okay, so will you have some time on the seminar today to talk a little bit in depth on?
Yeah, we'll try.
All right, good, thank you. So we'll make sure you actually understand it, and it actually gets better when you sort of try it by hand, literally try to do it, go over it. But again, the idea is, you try to map parameters of your model to the actual data, and there are various ways to do it. You can do it through least squares, you can do it, through many other approaches, but this method of максимального правдоподобия is sort of one of their standard and kind of stable with respect to noise approaches, and that's why it's being used a lot. But we'll dive into it in a lab session today.
Okay.
All right, so switching gears again, remember that the goal for today is to give you some instruments that will allow you to investigate networks, right? So the first instrument was this analysis of statistical properties, analysis of degree distribution, right? That's sort of the first thing you do as a statistics on the network you got. Okay, the second one, the second property we're going to address is this sort of connectivity of the graph, right? So, connectivity means you can get from point A to point B, in the graph. It's, think about, I don't know, going around the city in public transportation, right? So, changing buses and how far you can get. That's sort of the notion. Some graphs are connected, some are disconnected. A critical, sort of very important notion is a path, and the path from one node to another. A path from one node to another node is a sequence of edges that joins two vertices, right? So if I take node 3 and node 2, well, the path is here, edge 3 to 1, edge 1 to 6, edge 6 to 2. Now, a graph is called as connected if there is path between any two vertices. Like right here, I can pick up any two vertices, and there is always a path between them. I can take this vertex and this one, and there is a path, etc. Now, if graph is disconnected, you can always find the vertices that there is no path from and to. Like you take the number 4 and number 6, well, there is no way to get from one node to another. Now, those nodes belong to the same graph. So this is a graph, but it is disconnected. And in fact, it consists of what's called connected components. So there is one connected component, there is another connected component. Now, connected component is a subgraph where you can get from any node to any other node. Now, among those connected components, those connected components will be different in sizes, right? Like right here, this is much larger than this one. And we'll observe in the networks, and that will be another very interesting property, that there is usually one gigantic connected component that is much, much larger than any other component. We usually will sort of focus, we'll be interested in the largest one, right? Which is again gigantic connected component. That's what it's usually called. Here is an example. Again, this is the same graph we saw before. This is our gigantic connected component, right? Within this big component, we can get from any node to any other node. And these are smaller components, right? There are still nodes connected, but they're small. Notice that there is actually 92 components in this graph, 92 connected components in this graph. So 92 pieces we can get from, from 1 to 2. And the component sizes, this guy, like, significantly dominates everything else. And in the real world networks we're going to study, you will always see this kind of structure where one component size is much, 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 much larger than others. And so when you study this graph, one of the first things you want to do is to actually separate them, because a lot of algorithms we're going to talk about later, they require connectivity between nodes. Let's say if you want to find the shortest path from one node to another node, well, there might be somehow here, but if you request the shortest path in between, say, this node and this node, well, there is no way to get there, right? And your algorithm can get confused. So some algorithms handle it well, others do not. So it's a very, very good practice before you start sort of doing any algorithm that are related to finding path along the network, is to select and remove the gigantic connected component and work only with a sort of connected graph. When you do histograms, you don't care, right, if they're part of one big component or if they're parts of different components. But when you start studying, the geometrical structure of the graph, that becomes important. Okay. So the good news again is that that there is a way to do this. Oh, and I didn't show the command. Well, there is a command within iGraph. It's called connected components that actually does this for you, right? It can extract connected component. You just have to remember to do it. So the next important property is the distance between nodes and vertices. Now, when we talk about graphs, these are sort of abstract notion, right? And there is no geometric coordinates attached to the nodes. You know, even if we talk about, unless it's a very special type of graph, right? And so, you know, defining like distance in kilometers between two nodes doesn't make any sense. So you define the distance between two nodes as a number of, through the number of intermediate steps you need to make to get from one node to another node. And so distance between, say, you know, node 2, distance between node 2 and node 5 is equal to 1, right? There is one edge between them. Distance between, so, you know, it's 1. Distance between node 2 and node 4 is equal to 2. And in fact, you know, it's the shortest path, right? Distance between node 6 and node 1 is 1, 2, 3. Okay? So there are different distances. Now, graph can be characterized by either diameter or average path length. So diameter is a maximum, is the largest possible shortest path. Now, looking at this graph, what is the largest, what is the diameter of this graph? So it will be like longest, shortest path.
1, 2, 3, 4, 6.
But if you do go this way, right, it is the longest path, but it is not the longest, shortest path between them, right? Remember, there is another word here, shortest. So we need to go through all the pairs of nodes, find the shortest path between them, and take the largest of those. So in between node 1 and 6, this is the shortest path, right? Right. So, and this is a long, and like I can try to find the shortest path between node, let's say 2 and 6, it's going to be this one, right? Or this one, but in both cases, it's the length 3, right? And this one is also length 3. So for this graph, right, the diameter, which is the largest shortest path, is 3.
Yeah.
Make sense?
So it's largest from all shortest, from all distances.
Yes, it is largest among all the distances, right? Largest among all the shortest distances. So that's the graph diameter. Again, you know, computer will compute it for you, right? So, you know, but it's good to understand what it is. Now, another metric, it's called average path length. Now, if you look at the definition, average path length is with adding up all the possible path lengths between every possible node and just divided by, you know, the total number of those path lengths. So what I mean is the following. What you do is, okay, we take the distance between 6 and 4, which is equal to 1. We take the distance between 6 and 5, which is equal to 2. We take the distance between 6 and 3, which is equal to 2. We take distance between 6 and 1, which is equal to 3, and so on and so forth. And we do it for each and every node, and then we divide it by the total number of those paths. Now, do you think it's going to be greater than diameter or less than the diameter? It's going to be less, right? Because you know, you're adding this direct path, for example, right, which is much smaller. In fact, this metric is honestly much better description of a graph than diameter. Why? Well, because imagine, you know, I'll modify this graph a little bit. Let's say we have a few more nodes, right, in this graph. If I do this, if I add those nodes, then the diameter will be what? Like the longest path will be, longest shortest path will be 1, 2, 3, 4, 5, 6, right? Will be 6. So it's pretty large. But in fact, this graph is very compact. I mean, you know, it's kind of, everything is there, right? So if I calculate shorter average path lengths for this graph, it will be much smaller. It will probably round in between 2 and 3. I don't know exactly, but we can calculate that. And so average path length is stable with respect to having those long chains of nodes. In fact, if you compute both of them and they differ a lot, it tells you that there are some long chains present in your graph. It's again a way to learn something about a graph without drawing it. All right? So let me give you a few examples here. So this is the same yeast graph. This is the same yeast graph, the sort of the hairy ball, yellow hairy ball we saw in the previous slides. Actually, let me get to that graph for a second. Yeah, this is this graph. And what I'm trying to do is I'm trying to calculate all the shortest paths between all the nodes in the graph and build a histogram of those, which is just count how many paths of certain lengths are present within this graph. And so this is a histogram. And you realize if I just take all the pairs of nodes and calculate all the possible shortest paths among them, then majority of the nodes will be connected through 5 steps. Now, there will be some number of nodes connected directly, right? Some number of nodes connected through 2 or 3 steps, and some number of nodes required like 15 steps to get from one to another, right? And that's for the 15 steps would be those guys, on those, sort of this is the major graph, right? You take the node somewhere here, a node somewhere there, and that will be like sort of this very long pathway. So there will be a few of those, but majority is right here. So the average path length will be actually 5.1, but the diameter is 15. And so that tells you that within the graph, you will have this sort of core that is quite well connected, but then you will have this sort of chains of nodes getting out of the graph. And those chains will give you this long diameter. Make sense? All right. Hey, guys at the back of the room, does it make sense?
Yes.
Good. Okay. So, final topic for today is this clustering coefficient. Again, we touched upon it briefly last time. I just want to give you a precise definition so we can actually use the definition to compute those values. So the first definition is called local clustering coefficient. And this is a value you compute per vertex, per node. So it's a property of a node. The same way as we compute degree of a node, which is a number of neighbors, number of friends. Local clustering coefficient is a property of a node. Now, what does it tell us? So local clustering coefficient is actually, it tells us about the neighbors of a node. So when you have a node and you have 2 neighbors of this node, right? So you have 2 friends. The clustering coefficient really tells us what the probability that they are connected. Okay? And the way it's done, the way this computation is done is very simple. You look for all the connections, all the links among the neighborhood of the node, and divide by the possible maximum number. K is a node degree, right? So let's see how it works. If we look, for example, right now at this graph, and we're actually calculating this clustering coefficient for this very central node, okay? So the central node has 4 neighbors, so it has 4 friends, and neither of them know each other, right? There is no links between them. So these 4 guys is a neighborhood, well, we use that letter N, of this central node, and there's no links there. So the clustering coefficient for this guy is equal to 0 because neither of his neighbors are connected. Second picture. The same neighbors, but now they know each other. Let's take a look at this. So there are three edges connecting the neighbors. But what would be the total maximum possible of edges connecting the neighbors? Well, this edge is missing, this edge is missing, and this edge is missing. So the maximum possible connectivity here will be 6, but only 3 connections are present in the neighborhood. So the clustering coefficient is 3/6, or 1/2. All right? So it really tells you, like, okay, you have, 2 friends, if they're connected or not, right? But then you count actually all the possible connections between your friends. Like if you have 3 friends, there might be more than 2 connections between them. Now in here, we have the same story, but all the connections are present. So each friend knows each other in this situation. Like you have friends and each and every friend of yours knows each other. Then the clustering coefficient is 1. So you're in the center of all the possible triangles, right? Notice there is no triangles here, no triangles here, 3 triangles here, and 6 triangles here. So in some sense, what we're counting here when we're saying number of links in the neighborhood, because you are connected to those people, it means you're counting triangles with you or with this node in the center. So number of links here, 3, but you can also think about this as having 3 triangles all centered at this node, right? So it's number of triangles this node is part of. Now we can calculate, of course, this clustering coefficient for any other node. And for this node, clustering coefficient will be 0 because it's also not connected. I mean, it's connected to this node, but it's not connected to anybody else, right? And clustering coefficient will be different in here, right? Because it has 2 nodes and they're connected. So the clustering coefficient is 1. For this guy, it has 1, 2, 3 connecting nodes, but it's member of only 2 triangles, right? So out of 1, 2, and this third possible connection, it only has 2, so it is 2/3 for this guy, and so on. So you can calculate those. Local clustering coefficient is a metric of a node, right? It's a metric of how friends of a node are connected. Okay. Now you can actually take that. I mean, since it's a metric for each and every node, then of course you can calculate it across all the nodes, and you can sort of average out, right? And use this as what's called average clustering coefficient. But typically people, calculate it per node, and there is a way to do it using the command transitivity type local. As I mentioned, in the previous lecture, the network science is actually just becoming, science, and there are different people contributing to it, and sometimes, in attempt to describe the same phenomenon, people use a little bit different definitions. So along with local clustering coefficient, there is a notion of global clustering. Now, global clustering coefficient is a number that characterizes the entire network. All right? So if local clustering coefficient is a number that characterizes a particular node, then the global clustering coefficient characterizes the entire network. And the way it is introduced and computed is very simple. It is 3 times the total number of triangles in the network divided by the number of connected triples. So let me show what it means. Here, this is a triangle, this is a triangle, right? So to calculate it, we need to do 3 times the number of triangles, and there are 2 triangles. And triples here what we mean by triples is any of this kind of patterns, right? Oops, sorry. Right. So this is a triple. This is a triple. This is a triple. This is a triple. So pretty much any connection like that, right, of 3 nodes is a triple. And so what you do is divide the total number of triangles, 3 times the total number of triangles, by the number of connected triples. Again, this gives you just the ratio of the number of triangles to the total possible number of triangles. Now, if all the possible number of triangles present, then this coefficient will be 1. If less, then if not, then less. But it sort of tells you how much triangulated your graph is, right? So how much overall in the graph, friends of friends know each other. Now, unfortunately, and that's sort of the result of different people contributing, and science is just becoming a science. Those two, this global clustering coefficient and average clustering coefficient, when computed through all the nodes, they're slightly different. It's not the same number. So the rule of thumb is whenever you want to talk about individual nodes, you do this local clustering coefficient. Whenever we want to talk about the big picture, the graph itself, we're doing global clustering coefficient. And this example, by the way, showing you that this values, this C triangle is this global clustering coefficient, and this C average is from the previous slide. So the values will differ slightly. But in both cases, the more triangles you got in the graph, the larger this number is, right? So you want to get a feeling of how many triangles in there. You compute the number. You sort of know whether your graph is is strongly triangulated or not. And you can compute it by just calling the same function, transitivity function, with the parameter global. Okay. All right. This is again the same yeast graph, the same sort of graph, yellow crazy graph, where I calculated the local clustering coefficient and just counted how many of nodes have that value, right? And so notice there are quite a few nodes here that have value of 0, and that's because we have this type of connections in there. All those chains, they contribute to this value, which means friends are not connected. And there are some number of very well connected neighborhoods, right? This means clustering coefficient equal to 1 means that if you have, say, 3 neighbors, right, then there is always a connection in here, connection here, connection here, right? If you have 4 neighbors, there are more connections in there. And there are a bunch of things in between. So we can calculate sort of average in here. I didn't do it. I calculated global. It's 0.5. Again, that means the graph is kind of have a lot of triangles in it. This is again sort of a way to understand the graph without actually drawing it. The reason I'm sort of paying attention to this is because majority of the graphs that are interesting and that we sort of work with, they're very large, and you cannot just draw them and understand. I mean, it would be a great thing to draw the picture and sort of look at it, eyeball, and sort of, understand it. Unfortunately, in most of the cases, you'll not be able to do it, and so you need to understand it by calculating certain metrics and measures that probe the graph, right? And these are the probes, that you should be using. So to sum up, Now, this is a big table. I'm not expecting you to, I'm not even sure if you can see the number. Can you see the numbers on the big screen? Sort of? Yeah. Okay. Well, I'm not going to go into the details. You know, you'll have this presentation, and you know, then you can look it up. But the point I'm trying to make here is the following. These are all kind of different types of networks. We have social networks, we have information networks, sociological networks, biological networks. And these are very different types of networks. And these are sizes of networks. And you realize some networks have the size of like, 500. Some network has the size of like 700,000. And some networks have a size of millions. What's interesting here is the following. This parameter right here, it's called alpha, but this is a gamma we discussed, which is their parameter in the distribution, right? Px Cx minus power gamma. So this is that value in this column. Notice that for real graphs, it goes from, let's say, 2.3, 2.1, 3.2, 2.7, 2.5, 3.0, etc. So it is within the sort of 2, 3 region. The next one is a sort of clustering coefficient. And in fact, there are two of those because, as we discussed, there are sort of two versions of them exist. And you realize that some graphs are denser than others. Finally, right here, there's average path length. And some of the graphs, you notice, they have very small path length, 3.4, larger. Now, this dating graph is pretty large. Peer-to-peer network is 4, 2, 3. And this is an example of this small world problem, right? Remember, so we talked about small path lengths, small graph diameter, or path lengths being the small world, right? Sort of 6 degrees of separation, 6 рукопожатий, right? So this is an example of that. If you look at it, this is like million nodes, and it takes you only 16 steps on average to get from every one node to another. This is 1.5 million nodes. It takes you on average 5 steps to get from one node to another node, right? This is 500,000 nodes. It takes you 3.5 steps to get from, on average, from any node to any other node. So they're quite small. And what we did today is we looked at this metric, right? So we looked at the metric average node degree. We looked, I'm sorry, average path length. We looked at the metric that is that tells you, the power law distribution, and we looked at these two guys, which are clustering coefficients, right? And these are graph sizes. And if you notice, that's pretty much almost all the metrics that are being used to compare graphs. So now we can at least, you can look at these things and say, okay, now we know what that means. Or hopefully you can say that. I mean, that was my goal. Okay, to sum up and finish for today, power law degree distribution, and we looked at it, and we know how to find gamma. We know what gamma is in that formula, and we even looked at a little bit at how to get that gamma from from mathematics, and you'll talk about it more at the lab session. We talked about average path length, right? So we define this average path length and diameter, and we notice that in all those graphs, average path length is small, right? We talked about clustering coefficient, and we say, okay, well, actually there are two of those clustering coefficients, and it's local and global, and we see that in social networks they're pretty high. And we also notice that quite often we deal with gigantic connected components, when one component is much larger than the other. So these are the key properties of the complex networks, social networks that we're going to work with. And this is actually, an algorithm for you when you start investigating those networks. Literally, go through that and like put a check mark. Okay, you know, we check the distribution. Okay, it's power law. Great. Let's calculate average path length. Okay, here it is. Let's calculate clustering coefficient. Yes, there they are. And so if we get power law degree distribution, if we have a small world property, small average distance, and we have high clustering coefficient, yes, you are within this, you know, complex networks world, right? And there are a lot of properties that we're going to discuss further actually applies here. All right, that's it for today. That's the story. Very last slide, as usual, some reference to sort of original work and textbooks you can get more information about. Any questions? Yes. Sorry.
On the 27th slide.
Okay, just give me 1 second.
We've just watched it.
Yes.
I wonder why the clustering coefficients between the average one and the global one are really different in the value. So the question is there any physical sense between this high difference?
Very good point. Let me.
Something when I see like 008 and 06.
Honestly, I'm also quite surprised right now noticing, for example, this huge difference, right? I would be much more comfortable if the difference was like that, right? Which would be much smaller. Mm-hmm. So honestly, or when they're, you know, like this, honestly, I don't know any good you know, any good explanation of why it is where it is. It is slightly different definitions, and they play out differently depending on you know, the actual structure, right? This one just counts the number of triangles, right? This one looks at the local structure and then averages it out. I think there might be some research papers dealing with that, like sort of comparing it against each other on a different networks, but usual conclusion is that they're different, right? They just happen to have the same, you know, name, and they have the same feel. It tells you about, like, you know, how many triangles and how many connections among neighbors, but they're not the same thing, right? I recommend you to look up in the Barabashi book. I think there is a, you know, there are some comments there with references, or you can actually just Google compare, you know, this local clustering and global clustering coefficients, and you know, you might find some more insights.
I just thought it's like it might be something close, like when you calculate probability for some metrics, I don't know. Then if you do incorrectly, you can take average among probabilities, and then you get a wrong average. Well,
could very well be that's right. So when you do this kind of things, you also sometimes what's called double counting, because when you do triangles, you just count the triangles, right, for everybody else. When you do local, you actually count the values for your neighbors. But when you go for your neighbor, you take into account, you know, the one you already counted, so to speak, right? And so average is not exactly the same as just counting the number of triangles. Mm-hmm. Now, unfortunately, I don't know, like, sort of, you know, deep meaning of that difference.
Okay.
But I would say, you know, in practice, yes, both of them are getting larger when you know, you have more triangles and when the sort of connectivity is denser, right? And so that's what usually counts. But again, if you're interested, dig in. Next time, please tell us. I would love to hear that, if there is any, like, sort of deeper meaning in that difference.
Okay. I'll think about it.
Anything else? All right, cool. Then we're done for today. There will be a, you know, a lab, a seminar after this. And Ilya Andreevich, are you there?
Yeah.
Good.
Online listeners, we have additional link to classes Zoom.
All right, so you're gonna mail it out.
Yeah.
Right? All right, good. All right, guys. Well, thank you very much, and have a good weekend.
Thank you very much.
Thank you.
Bye from Boston.
Okay, we have 5 to 10 minutes break, and after that we'll start.